General safety rules. Be sure to read all fire alarm and safety signs. Ensure you are fully aware of your facility's building evacuation procedure. Make sure you know where your lab safety equipment, including first aid kit and fire extinguisher. Know emergency phone number to use to call for help in case of emergency. Open flames should never be used in the lab unless you have permission from a qualified supervisor. Do not work alone in the lab. Never leave an ongoing experiment unattended. Report all injuries, accidents, and broken equipment or glass right through, even if the incident seems small or unimportant. If you have been injured, yell out immediately and as loud as you can to ensure you get help. If you notice any unsafe condition in the lab, let your superior know as soon as possible. Housekeeping safety rule. Always keep your work areas tidy and clean. Make sure that all eye wash stations, emergency showers, fire extinguisher, and exit are always unobstructed and accessible. Only materials you require for your work should be kept in your area. Only lightweight items should be stored on top of cabinet. Dress code safety rules. Always tie back hair that is chin length or longer. Make sure that loose clothing or dangling jewelry is secure or avoid wearing it in the first place. Never wear sandals or other open-toed shoes in the lab. Footwear should always cover the foot completely. Never wear short or skirt in the lab. Personal protection safety rules. When performing laboratory experiments, you should always wear a smoke or lab coat. Before leaving the lab or eating, always wash your hands. After performing an experiment, you should always wash your hands with soap and water. Electrical safety rules. High voltage equipment should never be changed or modified in any way. Always turn off a high voltage power supply when you are attaching it. Use only one hand if you need to adjust any high voltage equipment. It's safest to place your other hand either behind your back or in a pocket. Function of oscilloscope. Oscilloscope front panel consists of CRT system control, horizontal system control, power, vertical system control, and trigger system control. Oscilloscope is the device for drawing calibrated graph of voltage versus time, used for the design and repair of circuits in which voltage and current can make a plot of change in almost any measurable quantity that are changing with time. The heart of oscilloscope is a cathode ray tube or CRT. It has two channels so that two different voltages may be plugged simultaneously for direct comparison and a variety of triggering options. The dotted lines are provided for post-thrust time measurement. The vertical system accepts input signals and develops appropriate deflection voltage for the CRT. The position control allows you to place the trace on the screen as desired. The red knob in the center of the control allows you to continuously vary the vertical scale factor. The BW limit bandwidth limit button allows you to cut off signal with frequencies higher than 10 MHz. Channel 1 signal is displayed for one full sweep. Channel 2 signal is displayed on the next sweep. The horizontal system controls the time scale of our clock. The trigger system is used to start successive sweeps at corresponding points on the input waveform on each successive sweep.
For this example, an oscilloscope will be used to measure the frequency and voltage of a signal. When measuring a single source, attach the lead to the channel 1 terminal and select the channel 1 mode.
Of your screen. So this bad boy is going to just connect in like this. So we're just going to set it there, and you can see there that now we've got a signal coming through on the scope. Turn your selector switch for the oscilloscope to channel 1. So I'm on channel 1 right now. That's where I have the connector connected into, but obviously if I go to channel 2, I've got nothing, right? Dual is going to be a combination of those guys and the addition of those guys. So we don't want to do that. We just want to keep things simple and look at channel 1. Beauty. Okay, next one. Adjust your volts per division to 1 volt per division so you can see a deviation between your peak lines. Okay, so this calibration connector that we've connected up to is 2 volts peak to peak at 1000 hertz. So what we need to do now is change the volts per division. Again, we're on channel 1, so changing this knob would not make any sense whatsoever. But changing this guy that corresponds to channel 1 will change the value that's on the screen. So you can see that as I change this value, now we're off the screen, and we're going to keep it at 1 volt per division. That way, if we have 2 volts peak to peak, then we'll be able to see the whole waveform on the screen. Okay, next thing, turn the variable volts division completely clockwise. So this definitely will screw you up during your lab.
The set of controls on the left of the oscilloscope vary the position and scaling of the vertical or voltage axis of the signal displayed on the oscilloscope screen. The vertical position dial is used to change the position of the signal's display relative to the grid. It does not alter the actual input signal. The volts per division dial changes the scale of the displayed signal voltage and can be used to ensure that the entire range of the signal is displayed on the screen. To calculate the peak-to-peak voltage of the signal, the number of divisions between the maximum and minimum of the signal must be counted. This value, multiplied by the volts per division setting, gives a peak-to-peak voltage. In this case, there are 5.6 divisions, multiplied by a volt per division of 1 volt, giving a peak-to-peak voltage of 5.6 volts. Adjusting the volts per division dial will change the size of the signal on the screen, but not the signal itself. With this alternate scale, there are 2.4 divisions, multiplied by a volts per division of 2 volts, giving a peak-to-peak voltage of 5.8 volts. The difference in the two readings is due to uncertainty. Always choose the scale appropriately. Make sure that the signal spans as much of the screen as possible, while still allowing you to measure. The set of controls in the middle of the oscilloscope vary the position and scaling of the horizontal or time axis of the signal displayed on the oscilloscope screen. The horizontal position dial is used to change the position of the signal's display relative to the grid. The time per division dial changes the timescale of the displayed signal and is used to ensure that an entire cycle of the signal is displayed on the screen. To calculate the period of the signal, the number of horizontal divisions between successive crests of the signal must be counted. This number, multiplied by the time per division setting, gives the period of the signal. In this case, there are 3.4 divisions, multiplied by a time per division of 10 microseconds, giving a period of 34 microseconds. From this, the frequency can be calculated as the inverse of the period.